Test. There we go.
Good morning, everybody. I hope you drank plenty of water yesterday and you had plenty of food, so you're feeling perfectly fine this morning. And you enjoyed breakfast, so ready for day 2.
So yeah, the agenda very similar to yesterday, except the keynote is in the afternoon, just before the end. So it's a closing keynote rather than an opening keynote. Everything as we were before. So for those of you who I know registered today, this is the big room. The other one is called the other room. And then you can either go up these stairs or up the stairs in the other room to get to the mezzanine for the workshops. The workshops is a separate track that runs alongside the talk track. So the sessions are in here and the workshop is up there. Lunch will be served in the other room. And also there's coffee and snacks and everything else there as well.
It's confusing.
It is confusing, isn't it? Yeah. Should be called this room and the other room, right? Yeah.
And the upper room.
And the upper room, yeah.
Anyway, sorry about that. Just to remind you, all the session abstracts, the bios, everything about the speakers will be online within the next few days of the conference. This is the link to get them. So all the speakers will provide us all their presentations. We recording everything. Unfortunately for me, that will be put online as well within the next 2 to 3 weeks. So everything will be available for you.
And of course, a big thank you to our sponsors. It's really important for us to, to be able to run this kind of conference with sponsors. So do make sure that you do go and talk to them. Thank you to F5 and SNCC as our platinum sponsors, JFrog, Veracode, Secure Code, Warrior, HackerOne, and Sonotype as our gold sponsors. Detectify, Areas, Risk, Contrast, Security, Equal Experts, and Avatar for our silver sponsors. So they're all out there in the expo hall. So please do go and speak to them and get your stamps.
Yes, so don't forget you've got your sponsor passport, get a stamp. You get all the stamps, you just bring it back to one of us, white t-shirt or the gray t-shirt or red t-shirt, and we will just process it. And at the end of the day, we will pick 3 winners for 3 iPads. They're real ones, it's not just a picture, so don't worry.
And I think they're 10-point-something inch now, so there's a 10% bonus this year on iPad size, yeah, for sure. So yeah, there's another thing which we kind of started off in Seattle, where we asked for different categories of awards to be given out. One is Outstanding DevSecOps Community, Most Effective DevSecOps Team, and Outstanding DevSecOps Community. Oh, there's 3. Okay, the other one is Individual. And what we did was we wanted to really give back to the community, give back to teams that were pushing DevSecOps. These are the finalists. So during the closing keynote tonight, we will be giving out those awards on stage. So good luck to all the finalists there as well.
And just don't forget, we've got a survey. The aim of this conference is it's made for you, by you. So just give us your feedback, good, bad. We've got a 5-minute survey. Just go to devseccon.com/survey, and that will allow us to actually tailor the event accordingly to what you wish or what you don't wish to see.
And that's pretty much it. Enjoy the conference, and do make sure you, even if you registered yesterday, please go and see the registration desk, because there are a whole bunch more DevSecCon shirts which landed a day late. So pick up your DevSecCon shirt. There's also a bunch of notebooks, a swag bag with some other details in there. You should also have another lunch ticket, so you can get that for the day. That's also at registration. Yeah, enjoy the conference. Have a great conference. Our first speaker today, let me introduce Matt Carroll up on stage. Big round of applause for Matt. So Matt is an infrastructure security engineer at Yelp, and Matt's session is a kernel of truth, intrusion detection and attestation with eBPF. So hopefully, we had some fun with this earlier. Hopefully this is going to work.
How many engineers does it take to arrange windows?
About 5, I think.
About 5.
Let's see.
Okay, that looks good. That also looks good. Oh my word, things are working. Who'd have thunk? Okay, I hope you've all had your coffee this morning, because I'm about to drop 57 slides on you and a live demo in 40 minutes like a stone-cold maniac. Okay. Okay, so a kernel of truth. Firstly, before we get into what I'm talking about, who am I? I think it's handy to give a little bit of context as to why I approach problems in the terrifying way that I do. My name's Matt. I'm an infrastructure security engineer at Yelp, so I work at the London office. I used to be a site reliability engineer, which is like a sysadmin, but with lots more YAML. And in my personal life, I'm also a hand-wringing Linux botherer. Just to touch on the infrastructure security engineer part, so as we heard of a lot of yesterday, it's very good to, oh, it didn't stop my timer, terrible. It's really good to concentrate on bringing secure defaults to a platform. As a second line of defense, if you can have a secure operating system, secure platform, everything like that, you're in a much better place. You're eliminating classes of vulnerabilities. So that's what I do. So what's this talk about? Basically, we built a supplementary intrusion detection system. I say supplementary because I've not threat modeled it yet as to how you could circumvent it, but I'm pretty sure it's good. But it's, we'll get into that. But it's basically about utilizing OS features as security features, and it's told roughly in the order that it happened. Additionally, some of the things I want to highlight here is like, part of this talk is not just the technical part, but also how to get a greenfield security project off the ground. Personally, I'm on a team that gives me a lot of agency and a company that gives me a lot of agency. But at the end of the day, Yelp is not a security company. That's not our product. There is some convincing the org to let you do things. And doing a greenfield security project is kind of a difficult thing. So part of that is treating defensive security like economics, which I'll get into a little bit later. If you want to get a project off the ground, sometimes you have to focus on delivering like that business value early on, much like any feature developer has to. So one of the ways to do this is just to glue together extant technologies to bootstrap your custom tools. But also, use your business logic to your advantage. So part of this is about the fact that Yelp are a web property, as I'm apparently about to get into. So Yelp are a web property. So a lot of this is based around the idea that lots of people will be making TCP connections into us, but we don't make that many out to the internet. So just hold that in the back of your head as to why we've done things the way that we have. So Yelp, you might not have heard of us because we actually operate primarily in North America, despite the fact that we've got engineering teams in London. Our mission is connecting people with great local businesses. So we've got a website, we've got an app, and it's basically about being able to find the sort of businesses you want to go to. It might be a restaurant, it might be a plumber, whatever. So we've got millions of businesses, 4.6 million active claimed local businesses as of June this year. Yelp users have written nearly 200 million local reviews. We have millions of photos. But the main reason that I'm telling you this, other than because I'm supposed to, oh yeah, also we're hiring, is that we have over 300 services, and that's in addition to a slightly more monolithic main application that's over 3 million lines of code. So most of this is Python. So the point of this being that as I promised in my talk proposal, and then subsequently read and went, oh my God, I've got to fit all of this in the talk. We basically run on most of our workloads on our own platform as a service. And so largely this is just like Python business logic around Mesos, Marathon, and Docker. We're actually migrating our backend towards Kubernetes. But the idea here is that developers should be able to deploy services on a common platform without worrying about all the guts underneath. So effectively, we've got a bunch of developers doing disparate things, working on disparate services, like I said, over 300 different ones, and they're deploying onto these common workload servers. So how do you stay on top of what server is supposed to be doing what? I mean, like, it used to be that, you'd have your batch server, and that might be running this one job that always reaches out to this one place on the internet. But now we've got this homogeneous computing environment. So how do you stay on top of what various pieces of the code base are doing? So one of the things that we use on the infrastructure security team is Amazon Guard Duty, because we're heavily invested in AWS. And what this does is it will tell you about anything that it thinks is machine learning, suspicious, between your EC2 instances and the internet at large. So let's just dive straight into an example. I don't know how well you can see this, but effectively this is an example of a guard duty, of some guard duty output, collapsed down a little bit. So what the description says, EC2 instance blah is communicating with a remote host on an unusual server port. So we dig in a little bit, and we see that, so with guard duty, you can dig into things like the tags and things for the EC2 instance. So it's pretty metadata rich in that sense. But you dig in and you see, OK, so this was a corp NAT host. So it's routing outbound traffic for other things. So it's kind of unsurprising, but whatever. And you dig in a bit more, and it says, OK, connection direction outbound. It's like, well, what do you expect? It's a NAT server. You dig in a little bit more, and we see the port is, wait, the port's 2222. Alternate SSH. Why are NAT server doing alternate SSH out to the internet? I mean, so where's this going? This is an ISP, China Mobile? It's going out to a consumer ISP in China. That's not good. Well, luckily, actually, after much digging on this particular alert, I discovered that Guard duty can sometimes get confused between the definitions of inbound and outbound, especially if some skiddy is scanning your public IPs and trying to brute force SSH with their source port as 2222. But it demonstrates an important thing, right? So when these alerts fire, and especially when they're just for things that are actually business as usual, we have to kind of figure out attestation from inference, because one of these alerts can fire, and I can log on to the box, and I'm like, oh, the process is gone. Like, it's not doing it anymore. So you have to look at things like what host class connected, what IP address or ASN did it connect to, what was on the other end, how long was the connection, what direction was it in, how many bytes were transferred. And you can see we're still not getting into the meat of what actually did that. So you can look at what the PS logs say, which obviously you don't want to do, because that's just a snapshot of processes over time. So likelihood is, A, you didn't catch it, and B, just because a process is running at the same time as a TCP connection doesn't mean anything. That's correlation, but it's not causality. So the problem is that context is lost as soon as an instantiating process ends. So like I say, we're trying to track down what's connecting out to the internet on a given host. We know what the host is, but we don't know what process it was. It could have been some of our code. It could have been a reverse shell. Who knows? And part of the problem here is that TCP IP is also very metadata lossy, especially because there aren't enough IP addresses to go around. So it causes some problems because it's got nothing to do with the process tree. So we were burning quite a lot of time on this. So every time one of these alerts fired, we'd do some investigation. And the longest investigations tended to be for the things that were false positives, because you're basically rummaging around to prove that to find something malicious, but nothing malicious actually happened. So what if we could reduce mean time to resolution for false positives? So some kind of log source that links a workload to a connection. And if we knew the actor or the workload, and we can call it business as usual, that'd be great. And this is where the economics of the thing comes in, because effectively, we can gather far more diverse metrics and far more different indicators of compromise if we don't have to spend quite so much time on the business as usual stuff. So it's basically making yourselves more effective as a limited team of people. So I looked into the problem space here. So basically at Yelp, we have 2 3-day hackathons every year where you can work on really important things like being the bassist in an electro dub outfit for 3 days, or you can work on really unimportant things like this. So I thought about the problem space here, and basically I decided, what it was that I would like to do to solve this problem. So when a guard duty alert fires, I want to be able to determine if it's a false positive quickly. I only want it for guard duty traffic, so not internal to our VPCs. So it follows on from that. I only want it for outbound TCP, so non-RFC 1918. RFC 1918 is the one with all of your 192.168 addresses, is basically dedicating IPv4 space for non-public routing. So I want the entire calling process tree so I can see full local causality. And it's also got to include process ownership information. And finally, it shouldn't require workload tooling. Now, if anybody's tried to add tracing into all of the applications across the org without starting like that from the get-go, you know that these migrations take ages, and they're pretty much impossible. So I was thinking, well, what do all of our applications have in common? Not even all of them run in Docker. Or in a containerizer, or on Pasta, for instance. But what they do all do is they all run on Linux. And the one thing that we can ask is the kernel. So I started looking at eBPF, and at least partly because it was a hackathon, and I just felt like doing that anyway. So what's eBPF? This is roughly my explanation of eBPF. It's when Linux kernel developers look at BSD's packet filter and think, is this a kernel tracing framework? So BPF originally comes from the BSDs. So it's the BPF part stands for Berkeley Packet Filter. It's an in-kernel VM accessed as a device. And this VM's got a limited number of registers, a limited number of instructions. So when bytecode is injected into this VM, one of the first things that happens is it's verified to see if there are any loops in it. You can't have loops in a BPF program, because if you're injecting code into the kernel at runtime and you've got an infinite loop in it, you've just hosed your machine instantly. So it was basically used for packet filtering. So I don't know if you've ever used FreeBSD, use the PF command for firewalling. That's what you're doing. So eBPF, the E stands for extended, although I like to pretend it stands for electronic, much like email, electronic BPF. So it's also an in-kernel VM, but it's in Linux. It's also been ported back to FreeBSD. It's got more registers than BPF, making it a little bit more powerful, a little bit more capable. But actually what it's used for is hooking syscalls and tracing and proxying sockets. And in-kernel packet filtering still. And that's only touching very lightly on the capabilities. To quote Brendan Gregg, who talks a lot about tracing frameworks for various operating systems, superpowers have come to Linux. One of the interesting things, actually, is I've heard of a use case, and I think this is Facebook. They actually use BPF where they compile the bytecode and inject it into their network interface cards. It is that blazing fast. And in our use case, actually, we could use this to dispatch K-probes for the TCP v4 connect syscall. So we're talking very specifically about outbound TCP IPv4. Now, you might ask, what about IPv6? Well, we run on Amazon. Amazon relies heavily on RFC 1918, so I'll leave that as an exercise to the reader. Yeah, it's basically kind of like having a coprocessor for introspecting on kernel state and actual processor registers and stuff like that. But the core part of this is it's on all of our servers, and it's very difficult to lie to. Then this is just an interesting point in here. So previously, when I'd done versions of this talk internally, I'd said that it doesn't allow backward jump instructions. If you remember the talk yesterday about GraphQL, talking about nodes and edges, what the kernel verifier actually does is it verifies that you don't have any back edges. Those are indicative of a loop inside the program. So one of the problems here is this is how you used to write BPF programs. This blows my mind. This is actually creating arrays of bytecode instructions and injecting them into the kernel in C. Now, if this had been the case, you can imagine I wouldn't have wanted to do this for a hackathon. But it turns out that there's actually a really fantastic toolchain called BCC, the BPF compiler collection. And what this does, roughly speaking, is it takes this gets a bit weird when you explain it. So it's basically like writing C, but in Python. You can see here that, so you've got some Python up the top here, all very lovely. And then you've got this variable BPF text equals, and then this long string literal. So this is just one of the BCC examples. This long string literal that looks a lot like some C code, but has some weird templates for doing things like BPF perf output and stuff like that. So what it is basically a Python library for for controlling injection of compiling and injecting bytecode into the kernel at runtime. And you can do some pretty weird shit with it, to be quite honest. So I looked at this, and I was like, OK, so my problem space here is I want process tree attestation for every outbound TCP v4 connect syscall. So in theory, I can just add BCC to Python's PS util, and that should work. I mean, surely that can't work, because if we offload messages to the Python daemon, this is just going to race condition, because TCP connections will be too fast, right? Well, no, actually. It just worked. And I was absolutely amazed by this. It took me like a day to get proof of concept. So we went on and we built pidtree-bcc. Why is it called pidtree-bcc? Because I lack any imagination whatsoever. It traces process tree, and it's written with BCC. Easy peasy. So how does this work? So we've got some pretty simple steps here. So first step, we take our BPF text, and we template it out. And this is actually pretty horrific, what I did here. So you've got your static string that's got all of your C code in. And I used some Ginger 2 templates to inject a bunch of YAML so that we could then take that without having any loops, compile it down, and inject it into the kernel. So the text is then verified and LLVM compiled. So basically, you need to actually compile at runtime, which creates some interesting problems, as I'll get into later. The bytecode is injected into the kernel, and then effectively any TCP v4 connect syscall, the unfiltered events are basically passed to userland code, and most notably, this includes the process ID. So the things that are passed to userland are process ID, the destination address, and the destination port. Passed to the userland code, and the userland code is basically a really simple Python daemon that just crawls the process tree and logs all of that metadata together. So how the hell does that work? So this is it's like some of the. So the way that the kernel probes actually work is you create both a hook on the entry to the function and to the exit of the function. So the thing which we need to do first is that on the entry to the function, we have all of the context that's actually passed to it. So most notably here, we've got this socket which is passed to the TCP v4 connect syscall. And we need to store that for later because it's not present in the context after the function is returned. So what we do is we build this BPF hash, and literally all this is a map between process ID and a socket. And what this kprobe does, literally just as the function is entered, it takes the process ID using some dark magic. I had a quick Google of how this works. I used GitHub search, and I found, like sort of sacrificed lambs and dark magic and things like that. Still have to determine how that bit works. But basically, you pull out the PID, and then you add to this hash process ID as the key, socket as the value. So that when we get to the return of the function, what we can do is we can pull out the return code, and that's literally from the so the PT regs thing up here is a snapshot of the process of the processor registers at the time, and that will include the return code for the function that's just returned. So we pull out the return code at the top there. We pull out the PID again using some dark magic, and then what we do is we pull out that socket again. So we look up the socket based on the PID. And first of all, if we don't get anything out, we basically return because we are erroneously in this code path. If the return code was not 0, that means that we failed to sync the TCP connection. It didn't actually connect, so we don't have a hope in hell's chance of tracing that anyway, because it will have returned instantly. The process won't exist. We can't crawl the process tree. There's no point. But if we get past all of that, we then introspect on our socket that we've just pulled out, and we can pull out the source address, the destination port, and then we can start running through some filters. So what the filters do is they so you basically specify in a YAML configuration file a set of networks which you don't want to see traffic from. So most notably, like, loopback's a good choice here because a lot of the TCP connections there will happen so fast you won't be able to catch them. Although, to be fair, actually it does catch the majority of them now, which terrifies me. So filters in kernel from Ginger2 templates, which iterate over subnets in YAML configuration. Events that don't get filtered are passed out to the userland Python daemon, and then we use psutil to crawl the process tree. And you probably can't see this very well, but what we've got down here, we've got the process ID, destination address, any errors found, the destination port, and then the rest of this under the proc tree key. It's basically an array of events, so, of processes. So effectively what we have at the moment, and this is really easy to add more metadata to, for each process we've got the process ID, we've got the command line, and we've got the username that basically owned that process. And what you can see is actually, so this is me connecting to Freenode, I think, with WeChat, and you can see it goes command line WeChat, then it's Zeesh, because that's the shell that was parenting the WeChat, then it's tmux, because I use tmux everywhere, and that is parented by init. So literally, one of the things that you'll always expect to see in this output is that the last thing has PID1. So the end, right? I mean, so that all worked, except it was a hackathon project. So all it did was print events to stand it out and could only match classful networks. And I developed it on my personal laptop. But I demoed this to my team and then went off on PTO for a few days. And when I came back, I discovered that they'd roadmapped it for productionizing in the next quarter. I was like, thanks, fellas. So the road to production. So the first thing that it didn't do very well, it basically would only match it would only match classful networks. And I couldn't figure out for ages why. And it's because I was trying to be really clever with bitwise network matching. If you can only live to serve as a warning to others, that's fine too. Like, don't try and be clever with bitwise network matching. And so this is the format for all of the subnet filters that we actually use. So what we're doing is we are literally just bitwise anding the subnet with the subnet mask. So this is in our configuration. And then we and the destination address, so this is for the actual event, with that same subnet mask. We check if they're equal. If they are, that means that the IP was in the subnet. Don't ever try and do it any different way. You will waste so much time. So whilst I was trying to bash my head against this, one of my coworkers was working on a data auth project. So this is basically about trying to ensure that all of our internal sensitive data streams are secured, and that you have to be authenticated and authorized to access them. And as part of this migration, we were trying to find the things that weren't using the client libraries we'd already tooled. Now, my coworker was pretty confident that all of these clients which he couldn't identify were running on a particular batch machine. So this is like our old legacy crap, which everyone has. And he basically asked me, do you think pidtree-bcc could help me out with this? And I went, yeah, I'm going to regret saying this, but I reckon by tomorrow I can have it matching ports instead of IP addresses and Dockerized for ad hoc usage. And by the next day, I actually did that. I was as surprised as anyone. And he found all of these unauthenticated clients. But this was actually a huge opportunistic step forward, because actually once I figured out that subnet stuff, I realized, well, hang on a second. Like, what's the quickest way to get business value out of this? Is to ship it at various places, right? And I could work on making it all beautiful and productionizable and having all of the dependencies installed by our configuration management and everything like that. But equally, we have Docker installed in a lot of places. Now, the thing about running this in Docker is it's a bit gnarly. So I'm literally about to tell you how I decided to do all of the things that everybody says not to do in Docker security best practices. But it's OK, because allegedly I'm a professional. So basically, because it was a hackathon project, I couldn't get it working quickly in Python 3. It's Python 2.7. I'm sorry about that. So, I mean, it was a nice way of containerizing that. But it basically needs some setup at runtime. And BCC is such a bizarre framework in the sense that the first thing you need is you have to have Linux headers installed for whatever kernel you're already running. This is because you are literally compiling against those headers at runtime to build that bytecode. I mean, this is a really nice way of just, OK, well, actually, every time we spin up the container, we can just install the headers. And the great thing is it means that on every server reboot onto a new kernel, you just get the right headers. So that was actually pretty cool. The other thing that we need to do here is we need to mount in debug-fs. This was largely because of the way that I had it messaging to userland, which was also nasty and horrible, which I'll get into later. I fixed it now, though, so it's OK. The other thing which we do, so we volume mount in etc password for UID mapping. This is a privileged daemon anyway, right? And now I know that a lot of you are feeling very, very itchy about the fact that it's running as root as well. It's privileged. It's got capadd sysadmin. It's using the host process ID namespace. It's less worse in some ways, not a lot, than just running a privileged daemon on the host. The only reason it's in Docker is it's a convenient deploy artifact for us because we're trying to get to production quickly so we can demonstrate some value in this thing. Mounting in etc password, the benefit of that is that then when your log streams come out, rather than saying what the UID was, it will literally just say username. Getting into this opportunistic deploy with Docker, like I say, we run our own PaaS anyway, and it currently uses Docker as the containerizer. So easy peasy, right? One of the other advantages here is that in terms of actually deploying it, all I have to do is in our configuration management say, OK, we've got a systemd unit file here, and we will make it pull the new version of the container and run the workload. Super easy. Very ugly, but super easy. And it means you don't have to install dependencies and everything like that. I already talked about this slide. I don't know why it's here. The other thing that we have is log aggregation set up for us. Basically, a previous project with Go Audit, which takes an absolute fire hose of exec VE syscalls, had already set up a secure logging pipeline for basically reading a FIFO and outputting to Amazon Kinesis. So this thing's called syslog to Kinesis. The great thing is it also adds a whole bunch of metadata around like what the host name was, what ecosystem it was part of, everything like that. This originally fed our Logstash to Elasticsearch SIEM, but we've migrated to Kinesis Firehose and Splunk this quarter, and it is lovely. So it takes maybe on the order of 30 seconds to get from the event occurring to the SIEM. This is not because eBPF is slow. eBPF is stupid fast, but it's a logging pipeline, right? So once we had all these pieces in place, I decided, well, let's do a dip test, right? It's easier to ask forgiveness than permission. So I rolled it out on 2 security dev boxes and watched the logs roll in. So the thing that astounded me is it had negligible performance impact. Like, I could not see in any particularly visible way that there was any performance impact of turning this stuff on. And as postulated, I think it's just that the cost of subnet filtering, like so doing those bitwise ands for each of the TCP v4 connect syscalls, it's just so much less than the cost of instantiating a TCP connection. TCP connections are really, really expensive. Lots of connections out to public Amazon IPs, however, were creating a lot of noise. And this was business as usual. And part of me was like, well, you know, we can hang on to this anyway. It's not doing us any harm. But I wanted to demonstrate actually the utility. We should be focusing on events that we are not expecting to see, right? So I thought, if only Amazon maintained some kind of list of their public prefixes. Oh, look, they do. So they host a JSON file with all of their IP ranges. The problem being that once I filtered down to just the regions and just the services that I knew that we'd be connecting into, there were over 400 networks matching our requirements, which, you know, is quite a lot. So I wrote a quick script to consolidate AWS net blocks, because I was like, well, I bet a whole bunch of these are probably next to each other. It's just a quick script. What it does, you can say what regions you want, what services you want. It will find from that JSON file all of the IP ranges that match that. It will smash them together and try and turn 400 net blocks down to something else. And actually, the thing is, it went from 400 down to just shy of 200. And when I saw this, I was a little bit disheartened, because I was like, you know, surely you can't load 200 net blocks into the kernel and compare all non-RFC 1918 TCP v4 connect syscalls to them in a performant manner. And there's only one way to find out, to be perfectly honest. This is the bit where I, very ill-advised, have actually got a video of this, but I'm going to try and do it live instead anyway. Let's see. So this is actual real infrastructure. So what we're going to do, google.com/hello-seccon London. OK, so what's just happened there is I've created a TCP connection to Google. And what we can see is like systemctl status, pidtree-bcc. So basically, pidtree-bcc is running here, and it's outputting to syslog to Kinesis, like I said. So if we do systemctl status, syslog to Kinesis, pidtree. That's it. Right. So effectively, like what this does is it literally just reads off of a FIFO and keeps dumping into Kinesis. As far as pidtree-bcc itself is concerned, this is like it's just logging to a file. It doesn't even know that it's logging to a FIFO here. So what I'm going to do here, Jesus, I hope this works. Let's try bringing this across. Hello? Hello? Do you want to? Oh, God, what's happened? How did this get here? I'm not good with computer. OK, right. Here's the moment of truth. It might not appear straight away because, oh, here we go. Thank God for that. It can take up to a minute sometimes. So I was like, am I going to have to tell a joke in the meantime? I know some pretty terrible jokes. So what we've got here is you can see I made a connection out to Google here. The process, so here we go, like this is the host I did it from. We've got the timestamp there. We can see process ID and port 80. So process tree here. Let's make this, see if we can't embiggen this a bit. OK, so where we've got process tree, we've got curlgoogle.com, hello DevSecCon London. We've got my username, that's it. You can see I'm using Zeesh again. I'm SSH'd in. There's an SSHD owned by root for me, and all the way up to systemd, all the way up to the init system. So going back to this, here we go. Where's my presenter view gone? There we go. Right, cool. So basically, like, this is a snapshot that I took of Sunday. Basically, we get like about 25,000 to 50,000 messages per hour across all of Devon Stage. We're currently rolling out to production at the moment. We're just setting up the container registries in production for it. I once accidentally load tested it at about 80,000 messages in 5 minutes from one host. That's because at Yelp, we don't use 192.168, except in Docker Compose, apparently, locally on machines. So we had one host that was absolutely spamming itself, and nobody noticed. The performance didn't degrade at all. The logging pipeline performed admirably, especially considering it was on our old Elasticsearch. And again, it just kind of verifies our assumption here. TCP connections are way more expensive than the filters are. So in the process of undoing my nasty hacks, because I committed a pretty cardinal sin in all of this, in the documentation for BCC says, there are various ways to get your message out to userland. One of them is BPF trace print K. Don't use that in production. That's for debugging only. So I happily went ahead and hand-hacked in my own JSON in the C code and printed it out to userland on the debug interface and shipped it to Devon Stage because I'm a bad person. But it meant that we were doing string manipulation in order to, so string manipulation in userland in order to pull that information out. Very recently, I pushed out a change where we're actually constructing some structured data in a ring buffer using BPF perf output. This has the advantage that the debug interface, so the one that I was mounting in earlier, is actually global to the OS. So you can only have one thing printing to it at any one time. I just happened to be the first person who got there. But now the great thing about this is it's now multi-tenancy, meaning that you can run multiple instances of pidtree-bcc on a given host. We've also added unit tests since. I've just written a branch for integration tests and trying to get them to pass on Travis, which is fun. But yeah, like I say, we're adding infrastructure for deploying the production environment. Incidentally, this also makes it faster. Where I was saying that like you can get like lots of race conditions on loopback addresses, this makes you get significantly fewer race conditions on loopback addresses because we're not passing around so much data, because like copying data between kernel and userland is actually very expensive. So future work here, I need to decontainerize it because that containerization isn't necessary. So actually having a Debian package would be really great. I have actually cut a branch where I do this crazy thing of exporting the Docker container out to a tar file system and then packaging it up with systemd unit file and using the unshare command to actually run the Docker container on a plain Linux kernel with no Docker install. Not that that's any use for anyone. I just wanted to see if I could. But anyway, yeah, migration to Python 3 because we want to be good open source citizens. Like, I'd like to add in things like, plugins for extra metadata gathering. So like a plugin for container awareness would be really good. So actually mapping from, the full binary path with the SHA in, we could probably use that SHA to query like Dockerd, or we could query some not network namespaces for Docker, but we can query various different pieces of information to actually pull out the friendly name for the container to attribute back to the service, and maybe start even fingerprinting what services make what connections out to the internet. I'd also really like to enable immutable login UID and start adding that in. So that's part of the audit CTL subsystem, and it's the idea that when you log in, you set what that login UID is. A privileged process will set that. If you set it to be immutable, it can only be set once, meaning that should you create a process and reown it to root and reown it to the init system, it will still show up that you did it. So like if I were to use my mad sudo powers to do some terrible nonsense, I would still get in the shit for it. Unfortunately, the man page for this cryptically says, but can cause some problems in certain kinds of container, which is very helpful. Yeah, and I'd like to do more threat modeling and hardening. Like I say, it's a supplementary intrusion detection system. It's to add metadata to your process. Additionally, I'd like to add some performance improvements. We don't really need to. It's fast anyway. And looking at more syscalls, so TCP listens, for instance, IPv6, UDP. I think we could probably feasibly do UDP session tracking in a BPF hash. And forwarded SSH socket reads from users that don't own them. There's so much you can add in here that's really, really high signal to noise. And also additional SIEM tooling. So for instance, when we get a guard duty alert in, I would like that IP address to be auto-matched to who actually did that thing. And that's it. We're hiring. We're actually trying to build a new team in London at the moment. If you want to come and work with me and do some mad shit, that would be great. Yep, that's the various. Come and find us. Come work with us. And thanks for listening. I don't think I have any time for questions.